Hi Bob, I've been diving into the quantum computing papers from November 2025, and there's quite a lot to unpack. I'm particularly curious about the progress on some of the fundamental challenges we've been facing. What caught your attention this month?
Hey Alice. Great timing. November was packed with interesting developments. One theme that really stands out is the continued battle against Barren plateaus in variational quantum algorithms. Yi and Bhadani's work on geometric optimization provides a fresh perspective on why neural network-assisted parameter generation helps overcome this problem. They show that parameters follow smooth, efficient paths that naturally avoid those flat training regions.
That's fascinating. So they're taking a geometric viewpoint rather than purely algorithmic? How does this compare to other mitigation strategies we've seen?
Exactly. What's clever is they're analyzing the parameter evolution on Lie groups, which gives them a principled way to understand why certain initialization schemes work. This connects nicely to another paper by Cho, Wang, and Yui on curvature-aware optimization. They model noisy qubit spaces using weighted projective lines and show that incorporating geometric information about hardware noise into the optimization process can stabilize training and mitigate barren plateaus.
So we're seeing geometry emerge as a unifying framework for understanding trainability? That's a powerful conceptual shift. What about the reinforcement learning approach by Rahul and Nguyen? How does that fit in?
Rahul and Nguyen take a different angle. They propose using negative learning rates to introduce controlled instability that helps escape barren plateaus. It's more of an optimization trick than a fundamental geometric insight, but it's practical for resource-constrained, quantum Internet of Things devices. The key is switching between positive and negative learning phases to recover significant gradients.
Interesting. And there's also that work by Yi and Bhadani combining classical PID controllers with neural networks, right? How does that compare?
Yes, their NPID approach is quite creative. They're essentially borrowing from classical control theory to stabilize quantum optimization. They show 2 to 9 times better convergence efficiency compared to other methods, with impressive robustness across different noise levels. It's a nice example of hybrid classical quantum thinking, where we don't necessarily need pure quantum solutions to quantum problems.
Speaking of practical quantum computing, I was really impressed by the work from Raisuddin and colleagues on benchmarking quantum chemistry. They used the W411 dataset with over 700 chemical processes on actual IBM hardware. What's your take on their findings?
That's one of the most comprehensive experimental studies we've seen. They ran sample-based quantum diagonalization for 16.85 hours on IBM Rensselaer, testing everything from atomization energies to nucleophilic substitution. The key finding is sobering. While they can achieve CCSD-level accuracy through extrapolation, they observe large statistical deviations and find that not all reaction types improve uniformly with more resources. Bond-breaking reactions show systematic improvement, but heavy atom transfers and nucleophilic substitutions don't.
So we're still far from uniform quantum advantage in chemistry. What about the work on unitary cluster Jastrow ansatzes by Lin and colleagues? I noticed they're trying to improve parameter initialization for chemistry applications too.
Right, Lin and colleagues address a related but distinct problem. The UCJ and LUCJ ansatzes are promising because they're hardware efficient, but truncating repetitions and accommodating connectivity constraints degrades the CCSD approximation. They propose 2 methods, using compressed double factorization to recover the CCSD approximation, and using approximate tensor network simulation to improve sample quality. Their results show significant improvements over standard Trotter-Suzuki decompositions, in some cases achieving higher accuracy with nearly half the gates.
It seems like there's a lot of focus on making quantum chemistry practical. How does the work by Brown and colleagues on generalized superfast encoding fit into this picture?
The generalized superfast encoding work tackles the fundamental problem of mapping fermionic operators to qubits efficiently. Traditional mappings, like Jordan-Wigner, produce high-weight Cauley terms that increase circuit depth. Brown and colleagues show that GSE, combined with path optimization and multi-edge graph structures, significantly outperforms conventional encodings for molecular simulations. They demonstrate a 2-fold reduction in RMSE for orbital rotations on IBM Kingston hardware. This is crucial because the encoding choice fundamentally affects everything downstream.
That makes sense. The encoding is the bridge between the physical problem and the quantum hardware. Shifting gears a bit, what's happening with quantum error correction? I saw several papers on that front.
Error correction saw some major developments. Goto's work on optimized many hypercube codes is particularly noteworthy. These are high-rate concatenated codes that can achieve about 30% encoding rate at concatenation level 3. Godot found that smaller variants using 6, 4, 2, and 422 codes can actually achieve lower block error rates despite higher encoding rates, and developed efficient fault-tolerant encoders with about 60% overhead reduction.
High-rate codes are crucial for making fault-tolerant quantum computing practical. What about the work on quantum LDPC codes? I noticed several papers on that topic.
Quantum LDPC codes are getting a lot of attention because they can dramatically reduce overhead compared to surface codes. Webster and Smith's work on explicit gadget construction for QLDPC codes is important. They show how to measure arbitrary logical Pauli operators with gadgets that reduce space overhead by at least an order of magnitude compared to surface codes. And Maurer and colleagues developed FPGA-tailored decoding algorithms, analyzing message passing, ordered statistics, and clustering approaches specifically for the constraints of real hardware.
The FPGA work is interesting because it acknowledges that decoding needs to happen in real time. How does that relate to the bounded error quantum simulation work by Kraft and colleagues?
That's a beautiful piece of work. Kraft and colleagues introduce a framework for bounded error quantum simulation that combines Hamiltonian and Lindbladian learning with uncertainty propagation. They demonstrated it on trapped ion simulators with up to 51 ions, showing that you can learn an open system model from early time data and then predict long-time dynamics with quantifiable error bounds. Crucially, they establish error bounds directly from experimental data without relying on classical simulation, which is essential for entering regimes of quantum advantage.
So they're essentially providing a rigorous framework for trusting analog quantum simulators. That seems like a critical step toward making these devices scientifically useful. What about the Google paper on reinforcement learning for error correction?
The Google work by Sivak and colleagues is remarkable. They unified calibration with computation by having the error correction process serve dual roles, detecting errors to correct the logical state and providing a learning signal for an RL agent to continuously adjust control parameters. They demonstrated 3.5-fold improvement in logical error rate stability on superconducting processors and showed through simulation that the optimization speed is independent of system size. This is a paradigm shift. The quantum computer learns to self-improve from its own errors during computation.
That's incredible. It's like the computer is doing its own online calibration. Speaking of surface codes, I noticed Paler's work on bridging, braiding, and lattice surgery. What's the significance there?
Paler's work establishes a systematic translation between braiding and lattice surgery representations using ZX calculus. The key insight is that both paradigms can be uniformly expressed as compositions of multi-body measurements, and the Rausendorf compression rule encompasses all known optimizations. This provides a foundation for automated verification and compilation of surface code computations, which is essential as we scale up. Plus, they introduce a novel Knot circuit with lattice surgery.
This EX calculus keeps proving useful. Now I'm curious about the work on distributed quantum computing. What's happening there?
Distributed quantum computing saw interesting developments. Sergeyev and colleagues proposed a multi-agent reinforcement learning approach for quantum architecture search, where each agent acts on its own circuit block. This allows much better scaling than single-agent approaches. And Zhang and colleagues built SimDisQ, the first end-to-end circuit-level simulator for distributed quantum computing that models heterogeneous backends and noisy connections. Both address the reality that future quantum computers will likely be networks of smaller processors, rather than monolithic devices.
That makes sense given the physical constraints. What about the work on quantum architecture search more broadly? I saw Ravara and colleagues had something on QUBO formulations.
Ravara and colleagues address a practical problem. Conventional auxiliary variable selection for QUBO formulations doesn't consider hardware connectivity, leading to high compilation overhead. They propose selecting auxiliary variables to construct interaction graphs with regular structure and limited vertex degree, which can be mapped efficiently to various architectures. They demonstrate almost 40% reduction in circuit depth compared to conventional methods. It's another example of co-designing algorithms with hardware constraints in mind.
Hardware awareness seems to be a recurring theme. What about quantum machine learning? I noticed several papers on that front, including work on non-stabilizerness estimation.
Quantum machine learning had some interesting developments. Lepardi and colleagues used graph neural networks to estimate non-stabilizerness in quantum sockets, measured by stabilizer Renyi entropy. They showed that GNNs can capture meaningful features from graph-based circuit representations and generalize well across diverse scenarios. This is useful because non-stabilizerness is a fundamental resource for quantum advantage, and efficient estimation is beneficial for practical applications.
And there was work on quantum reinforcement learning too, right? How's that progressing?
Lazaro and colleagues did a systematic dissection of parameterized quantum circuit-based quantum reinforcement learning, evaluating data embedding strategies, ansatz design, and post-processing blocks. They found that output reuse, though purely classical, exhibits distinct behavior in hybrid pipelines, and that data re-uploading improves trainability while stronger entanglement can actually degrade optimization. It's a good reminder that more quantum doesn't always mean better. You need the right balance.
That's a valuable lesson. What about applications to finance? I saw a couple papers on that.
There were two interesting finance papers. Gong and colleagues introduced the Quantum Network of Assets framework, using density matrix representations to capture non-classical correlations in financial markets. They define an entanglement risk index and quantum early warning signal that can detect structural transitions before price movements. And Soloviev and Krompiak tackled portfolio optimization using polycorrelation encoding, demonstrating that gate-based variational algorithms can handle over 250 variables by assigning multiple variables per qubit.
So quantum methods are finding applications beyond the obvious scientific computing domains. What about quantum communication and cryptography? Any major developments there?
Several papers addressed quantum key distribution. Treplin and colleagues did a comprehensive finite size analysis of decoy state BB84 with advantage distillation, showing that AD increases the maximum acceptable QBER from about 9.5% to 17.3%. Scarinzi and colleagues optimized information reconciliation for satellite downlink QKD, improving efficiency by leveraging a priori information about instantaneous QBER. And Sands and colleagues presented an adaptive security framework combining QKD and post-quantum cryptography for real-world heterogeneous networks.
The hybrid QKD-PQC approach makes sense given that we can't make everything quantum-enabled immediately. What about quantum hardware itself? Any interesting developments?
Loreto and colleagues provided a comprehensive review of deterministic quantum dot single photon sources, which are becoming commercially available with performance approaching ideal specs. They explain the operational principles and show that quantum dots and photonic crystal waveguides offer the best combination of suppressed leaky modes and per-cell enhancement. This is important infrastructure for photonic quantum computing and communication.
Speaking of hardware, what about the computational electromagnetics work for superconducting circuits? That seemed quite technical.
Elkin and colleagues provide a practical review of computational electromagnetics methods for superconducting circuit quantum devices. The key challenge is that these devices span nanometer to centimeter scales, which stresses the capabilities of standard CEM tools. They discuss the fundamentals of major CEM techniques and provide guidance on alleviating challenges related to multi-scale modeling. It's more of a tutorial for practitioners than a research breakthrough, but it's valuable for the community.
That kind of practical guidance is important as the field matures. What about quantum algorithms more broadly? Any interesting theoretical developments?
Several interesting algorithm papers appeared. Assi and colleagues proposed variational product formulas as an alternative to Trotter-Suzuki decomposition for quantum simulation, deriving parameters from a global action principle. They show improvements of factors of 2 to 5 in error reduction while sometimes reducing gate count by nearly half. And Barren and colleagues introduced tensor network algorithms for efficient state preparation of multivariate functions, demonstrating preparation of a 17-dimensional Gaussian in 102 qubits by simulation and a 9-dimensional Gaussian on 54 qubits experimentally.
State preparation work is crucial, since that's often a bottleneck. What about the work on quantum search with wildcards? That seemed like a nice theoretical result.
Cornelissen and colleagues generalized the search with wildcards problem, where you can test equality of subsets of an unknown bit string. They showed near-tight bounds for various query models including bounded size sets, contiguous blocks, and prefixes. The interesting methodological contribution is that they used the primal version of the negative weight adversary bound, typically used for lower bounds, to show new upper bounds without explicitly using SDP duality. It's a nice example of how quantum query complexity theory continues to develop new techniques.
Query complexity remains a rich area. Now I'm curious about the work on magic and non-stabilizerness. There seem to be several papers on that theme.
Magic as a quantum resource got significant attention. Bejan and colleagues studied magic spreading under unitary Clifford dynamics, showing that while total magic is conserved, its spatial distribution can be inferred from a canonical representation called the bipartite magic gauge. They found that magic delocalizes after initial ballistic growth. Zhang and colleagues introduced mutual mana as a measure of magic correlations, showing that coupling a magic state with a stabilizer vacuum via a discrete beam splitter converts local magic into mutual mana. And Ahmad and colleagues experimentally demonstrated non-local magic on a superconducting processor with up to 51 qubits.
So we're getting both theoretical frameworks and experimental demonstrations of magic as a resource. What about the work on quantum sensing? I noticed a paper on that.
Alexander and Mahesh demonstrated quantum sensing via large spin clusters in solid-state NMR. They created and manipulated clusters of correlated nuclear spins to sensitively detect pulse width jitters at the tens of nanoseconds level. The key finding is that there exists an optimal maximum coherence order that maximizes sensing efficiency, balancing enhanced sensitivity against decoherence susceptibility. They also supplemented experimental results with quantum Fisher information calculations.
That's a nice application of quantum metrology principles. What about more foundational work? I saw papers on topics like the Born rule and measurement incompatibility.
Agrawal and Wilson derived the generalized Born rule from first principles using a process-theoretic approach, showing that any process theory with basic compatibility axioms is equivalent to one where the Born rule holds. McNulty developed a graph-theoretic framework for quantifying measurement incompatibility, associating anti-commutativity graphs to sets of observables, and showing that incompatibility robustness becomes a graph invariant. These are nice examples of how we're still developing deeper understanding of quantum foundations.
Foundations remain important even as we push toward applications. What about quantum compilation and optimization? There seem to be several papers on making things more efficient.
Compilation saw several advances. Ricciardi and colleagues tackled equivalence checking of hybrid quantum circuits through deferred measurement, significantly outperforming prior work. Yang and colleagues developed ReQISC, a reconfigurable quantum instruction set computer that can implement arbitrary 2-qubit gates with optimal duration, achieving 4.97-fold reduction in pulse duration compared to CNOT-based schemes. And Wu and colleagues provided a comprehensive framework for quantum design automation, emphasizing co-design opportunities across the full stack from chips to algorithms.
The design automation work seems particularly important for scaling up. What about resource estimation? I know that's crucial for understanding when quantum computers will be practical.
Khalid and colleagues did important work on decoder latency impacts for utility-scale quantum computers. They built a model incorporating parallel space and time window decoding with realistic communication latencies, showing that even sub-microsecond decoding introduces substantial resource overheads, roughly 100K to 250K additional physical qubits for magic state factory storage, and 300K to 1.75 million extra qubits for increased code distance. For circuits with 10 to the 6 to 10 to the 11 T gates, runtime increases by roughly a factor of 100. This quantifies the real cost of fault tolerance.
Those numbers are sobering. It really emphasizes how far we still have to go. What about the work on early fault-tolerant quantum computing? I saw a couple papers on that.
Zhang and colleagues proposed error-structured tailored fault tolerance, designing one fault-tolerant continuous angle rotation gates that circumvent T-gate compilation and distillation. Their approach reduces space-time resource costs by factors of 1,337.5 compared to 15-to-1 magic state distillation. Sharma and Murali developed space-time optimizations specifically for early FTQC systems, showing that simple greedy heuristics can achieve 60% reduction in qubits with only 1.2x overhead in execution time. Both papers recognize that early fault-tolerant machines will operate under stringent resource constraints.
So there's recognition that we need techniques tailored to the constraints of near-term fault-tolerant devices, not just asymptotically optimal schemes. What about quantum simulation more broadly? Any other interesting work there?
Ogner and colleagues introduced resolution refinement for quantum state preparation, bootstrapping from low-resolution to high-resolution Hamiltonians through adiabatic evolution. They demonstrated it on few-body ground states, Hartree-Fock nuclear states, and Hubbard model states. Bengoechea and Over presented quantum time-marching algorithms for linear transport problems with arbitrary boundary conditions. maintaining linear time complexity with optimal success probabilities. Both show how to make quantum simulation more practical for specific problem classes.
There's a lot of work on making quantum algorithms more practical and efficient. What about quantum information theory more broadly? Any interesting theoretical developments?
Zhang and colleagues extended quantum thermodynamics to information processing with initial correlations, generalizing the second law and deriving a dynamical version of Landauer's bound. Din and Guillaume presented quantum algorithms for computing maximal quantum F divergences and Kubo-Ando means, providing a universal framework that includes Rényi entropy and matrix means as special cases. These contribute to our understanding of quantum information theoretic quantities.
What about educational aspects? I noticed a paper on teaching quantum computing.
Krutz and colleagues reviewed a practical course where graduate students implement quantum circuit simulators using different methods, state vectors, density matrices, stabilizer formalism, and matrix product states. The hands-on approach helps students develop deeper understanding of fundamental concepts like superposition, entanglement, and noise effects. It's a good reminder that as the field matures, we need to think about how to effectively train the next generation of quantum researchers and engineers.
Education is crucial for field development. Now, looking across all these papers, what do you see as the major themes or trends?
Several clear themes emerge. First, there's strong emphasis on hardware-aware compilation and optimization, recognizing that algorithms must be co-designed with hardware constraints. Second, we're seeing sophisticated approaches to Barren plateaus and trainability, drawing on geometry, control theory, and machine learning. Third, there's growing maturity in error correction, with practical schemes for QLDPC codes and high-rate codes. Fourth, there's recognition that early fault-tolerant systems need specialized techniques, not just asymptotically optimal schemes. And fifth, there's increasing focus on making quantum advantages concrete and quantifiable through careful benchmarking and resource estimation.
Those are great observations. What about the interplay between theory and experiment? How well are they connecting?
We're seeing much better connection between theory and experiment. The bounded error quantum simulation work provides rigorous frameworks for trusting experimental results. The Google reinforcement learning work demonstrates sophisticated control on real hardware. The quantum chemistry benchmarking provides honest assessment of where we are versus where we need to be. And the work on quantum dot sources shows technology maturing toward commercial availability. There's less hype and more careful quantitative assessment of what's actually achievable.
That maturity is encouraging. What about the diversity of application domains? What's your take on that?
The application diversity is impressive. Chemistry, finance, cryptography, machine learning, sensing, materials discovery, and even legal theory. But I think we need to be careful about distinguishing between genuine quantum advantages and classical problems dressed up in quantum language. The finance applications using density matrices to model correlations are interesting, but it's not clear they require quantum hardware. The quantum chemistry work is more convincing because it's running on actual quantum processors and comparing against classical benchmarks.
That's a fair point. We should be rigorous about what actually requires quantum hardware. What about the machine learning applications? There seem to be quite a few papers on quantum machine learning.
The quantum machine learning landscape is interesting but mixed. Zhang and Cerezo provide a balanced primer, noting the tensions between practicality and guarantees, and flagging where evidence is strong versus where it's still lacking. The work on adversarial robustness by Naomi and colleagues shows that quantum models face similar security challenges as classical ones. And the reinforcement learning work reveals that more quantum structure doesn't always help. You need the right balance. I think we're past the initial hype phase and entering more careful evaluation of where quantum ML actually provides advantages.
So there's healthy skepticism developing. What about the work on quantum advantage more broadly? How are people thinking about demonstrating and quantifying it?
There's increasing sophistication in how we think about quantum advantage. Zindorf and colleagues use macro-realism violation as a benchmarking metric, showing quantum to classical transition as system size increases. Abu Ghanem demonstrates pattern-dependent performance in the Bernstein-Vazzarini algorithm, revealing dramatic performance gaps between noisy simulation and real hardware. And Babush and colleagues from Google outline a 5-stage framework for developing useful quantum applications, emphasizing the need to identify concrete problem instances and connect them to real-world use cases. The focus is shifting from abstract speedups to practical, demonstrable advantages.
That shift toward practicality seems healthy. What about some of the more exotic or speculative work? Anything that caught your eye there?
A few papers explore interesting connections. Godfrey and Sickelman draw parallels between quantum entanglement and legal concepts, using quantum formalism to model how legal concepts can be entangled, such that changing one instantly affects another. Wang and colleagues use the spin-ZX calculus to bridge quantum computing, condensed matter physics, and quantum gravity. And Weinstein offers an epistemological reinterpretation connecting Heisenberg and Schrödinger's approaches to the P versus NP problem. These are more philosophical explorations than practical advances, but they show how quantum thinking is influencing other domains.
Those interdisciplinary connections are fascinating, even if speculative. What about the work on quantum protocols and primitives? Anything interesting there?
Several papers develop new protocols. Ganguly and Chaudhary introduce computational quantum anamorphic encryption, enabling covert messages within ciphertexts. Shmuley and Jandry work on unclonable cryptography with reduced quantum memory requirements. Bratley and colleagues present a general machine learning algorithm for quantum teleportation that creates optimal unitary operators for any system with well-defined measurements. These show continued development of quantum communication and cryptographic primitives.
The cryptographic work is important given quantum computing threats to classical cryptography. What about the work on quantum data quality and anomaly detection? That seemed like an unusual application.
Gropey and colleagues explore quantum computing for data quality enhancement, particularly anomaly detection. They demonstrate quantum reservoir computing for detecting volatility regime changes in stock market data, showing that quantum-based embeddings can be competitive with classical ones. The classification error rates are below 3.5% on Cella-based spoof and under 8.2% on WFAS datasets. It's an interesting application area, though it's not yet clear whether quantum approaches will provide significant practical advantages over classical methods for these tasks.
It seems like many application areas are still in the proof-of-concept stage. What about the work on quantum circuit properties and universality? I noticed a couple papers on that.
Iwakiri and Kano showed that the problem of simulating major classes of hardware-efficient ansatses is BQP complete, demonstrating that any relevant quantum circuit can be efficiently represented as an HEA circuit. Bruckmann and colleagues established a natural description of logical operator spaces for tile codes, showing they admit canonical symplectic bases of logical operators and introducing derived automorphisms that enable fault-tolerant gate implementation. These results deepen our understanding of quantum circuit structure and capabilities.
The tile codes work is interesting. They seem like a promising alternative to surface codes. What about other alternative approaches to quantum computing? Anything notable there?
Ahsaninejad and colleagues showed that realistic, normalizable GKP states can enable universal quantum computation using only linear optical elements. The key insight is that Gaussian operations on normalizable GKP states, combined with homodyne measurements, permit both Clifford gates with high fidelity and probabilistic non-Clifford gates. This demonstrates that normalizable GKP stabilizer states provide a practical framework for measurement-based quantum computation in continuous variable settings.
Continuous variable quantum computing remains an interesting alternative path. Looking at everything we've discussed, what do you think are the most important open challenges going forward?
Several key challenges stand out. First, we need better understanding of when quantum advantages are structurally possible versus when they're just computational speedups that might disappear with better classical algorithms. Second, we need more sophisticated approaches to error correction that work with realistic hardware constraints and noise models. Third, we need to bridge the gap between small-scale demonstrations and utility-scale applications. The resource requirements for fault tolerance remain daunting. Fourth, we need better integration of quantum and classical computing, recognizing that hybrid approaches may be optimal for many problems. And fifth, we need more rigorous benchmarking and honest assessment of where we are versus where we need to be.
Those are all critical challenges. What gives you the most optimism about progress?
What's encouraging is the increasing maturity and sophistication of the field. We're seeing more careful resource estimation, more honest benchmarking, more hardware-aware algorithm design, and more rigorous theoretical frameworks. The work on bounded error quantum simulation, reinforcement learning for error correction, and decoder latency analysis shows we're grappling with real practical challenges rather than just chasing abstract speedups. The diversity of approaches from QLDPC codes to continuous variable systems to distributed architectures suggests we're exploring the solution space thoroughly. And the integration of ideas from control theory, machine learning, and classical optimization shows healthy cross-pollination of ideas.
I agree, the field is definitely maturing. What about the interplay between near-term NISQ devices and longer-term fault-tolerant systems? How do you see that evolving?
That's a crucial transition period we're entering. The work on early fault-tolerant quantum computing recognizes that the first fault-tolerant devices will be severely resource-constrained, requiring specialized techniques rather than asymptotically optimal schemes. The reinforcement learning work shows how NISQ devices can learn to self-improve during computation, and the benchmarking work on quantum chemistry helps us understand what's actually achievable on current hardware. I think we'll see a gradual transition, where techniques developed for NISQ devices inform the design of early fault-tolerant systems, rather than a sharp discontinuity.
That gradual transition makes sense. What about the role of classical computing in quantum algorithms? That seemed to be a recurring theme.
Classical computing plays a much more sophisticated role than just pre- and post-processing. The work on neural network-assisted parameter generation, PID controllers for optimization, and reinforcement learning for error correction all show classical intelligence guiding quantum computation. The hybrid, quantum classical approaches to portfolio optimization and machine learning recognize that the optimal solution often involves both paradigms. And the work on classical simulation of Clifford circuits shows that understanding what classical computers can do efficiently helps us identify where quantum computers are truly needed. I think the future is much more about intelligent integration than pure quantum approaches.
That's a really important point. It's not about quantum versus classical, but about optimal integration. Well, this has been a fascinating discussion. Any final thoughts on November's papers?
November 2025 showed a field that's maturing rapidly. We're seeing more rigorous benchmarking, more sophisticated error correction, more hardware-aware algorithm design, and more honest assessment of challenges and limitations. The diversity of approaches and applications is impressive, but there's also healthy skepticism about where quantum advantages actually exist. The integration of ideas from control theory, machine learning, geometry, and graph theory shows the field is drawing on deep mathematical and computational foundations. Overall, I'm optimistic that we're making real progress toward practical quantum computing, even if the timeline remains uncertain.
I couldn't agree more. Thanks for the insightful discussion, Bob. It's been really helpful to get your perspective on all these developments. The field is definitely moving in exciting directions, and I'm looking forward to seeing how these ideas develop further.